Hello friends, I welcome you in lecture number 3 on Laplace transform. In this lecture we will discuss linearity property of Laplace transform, and then we will discuss Laplace transform of hyperbolic cosine and hyperbolic sine functions. So first we understand what is linearity property. So suppose we have two functions, say f of t and g of t, and suppose a and b are constants, they are any real numbers. Then suppose we want to find out Laplace transform of a times f of t plus b times g of t. Then linearity property says that Laplace transform of a times f of t plus b times g of t equal to a times Laplace transform of f of t plus b times Laplace transform of g of t. So we can prove this property. Before that we have written this property here, linearity property of Laplace transform. For any functions f of t and g of t whose Laplace transforms exist, and for any constants a and b, Laplace transform of a of t plus b gt equal to a times Laplace transform of f of t plus b times Laplace transform of g of t. We can prove this linearity property simply using the definition of Laplace transform. So we start from left hand side, and by definition of Laplace transform we can write Laplace transform of a into f of t plus b into g of t equal to improper integral from 0 to infinity e raised to minus st times this function a into f of t plus b into g of t. So this is by definition of Laplace transform. Now this is equal to 0 to infinity. This we can rewrite as a times e raised to minus st into f of t plus b times e raised to minus st into g of t. Integral is with respect to t. Now we know that integral is a linear operator, so we can write integral of addition of two functions equal to addition of integrals of these two functions. So this is equal to integral of function a times e raised to minus st ft plus integral of another function b times e raised to minus st times gt. Integral is with respect to t, and we can take terms which are independent of t outside integral. So this we can again rewrite as a times integral from 0 to infinity e raised to minus st times f of t dt, and here b is independent of t, so we can take it outside integral, and integral of e raised to minus st times g of t dt. Now if we observe, this is nothing but Laplace transform of function f. This is by definition of Laplace transform of f of t, and similarly by definition of Laplace transform, here we have Laplace transform of the function g. So therefore we have proved that Laplace transform of a into f of t plus b into g of t is equal to a times Laplace transform of f of t plus b times Laplace transform of g of t, where a and b are any constants. Now this property is true for n number of functions. Instead of only two functions, we can generalize this property to n number of functions and n constants. Suppose we have n functions f1, f2, fn, and they are multiplied by n constants a1, a2 up to an, then also linearity property is correct. So suppose I have n functions of t denoted by f1, f2 up to fn, and a1, a2 up to an are constants, then linearity property says that Laplace transform of this linear combination is equal to a1 times Laplace transform of first function, that is f1t, plus a2 times Laplace transform of second function, which is f2, plus a3 times Laplace transform of third function, that is f3, and so on, an times Laplace transform of nth function, which is denoted by fn. So this linearity property is helpful in finding out linear Laplace transform of linear combination of some functions. Suppose we are interested in the Laplace transform of 3 into e raised to 2t plus 7, then we know that linearity property is correct, and here we can rewrite this as 3 into e raised to 2t plus 7 into 1, and using linearity property this is equal to 3 times Laplace transform of e raised to 2t plus 7 times Laplace transform of 1. This is by linearity property. Now we have shown in earlier lectures that Laplace transform of e raised to at is equal to 1 divided by s minus a, and Laplace transform of 1 is 1 by s. So using that formula, Laplace transform of e raised to 2t is 1 divided by s minus 2, and Laplace transform of 1 is 1 by s. So this is equal to 3 divided by s minus 2 plus 7 divided by s, and if we wish we can simplify this. We take LCM as s into s minus 2, and here we have 3s plus s minus 2 into 7, that is 7s minus 14. So this is going to be 10s minus 14 divided by s times s minus 2. So this is the linearity property which is helpful in finding Laplace transform of linear combination of given functions. Using linearity property we can find out Laplace transform of hyperbolic functions also. We are familiar with the definition of hyperbolic, cosine and sine functions. We have written this just to recall those definitions. Hyperbolic cosine function is denoted by cos h space t equal and is defined as e raised to t plus e raised to minus t divided by 2. And if we take negative sign, we have sine hyperbolic t. And be careful, write hyperbolic function in this way: cos h, then space, and then t. Don't write hyperbolic function in this way, cos ht. This is not hyperbolic function, it is cosine of h into t. And when we write this, this means it is hyperbolic cosine of t. So there is a big difference in the notation. So be careful, whenever we are using hyperbolic cosine, we will write COSH, no space between these letters, then one space and then t. So this denotes hyperbolic cosine of t and is given by e raised to t plus e raised to minus t divided by 2. Similarly, sine hyperbolic t is given by e raised to t minus e raised to minus t divided by 2. And we can find out Laplace transform of these two hyperbolic functions using linearity property. So they can ask you this type of questions: prove that Laplace transform of cos hyperbolic at is equal to s divided by s square minus a square, and Laplace transform of sine hyperbolic at equal to a divided by s square minus a square. So we prove both of these one by one. First we find out Laplace transform of cos hyperbolic at. So first we replace cos hyperbolic at by the definition. It is e raised to at plus e raised to minus at divided by 2. This is by definition of Laplace transform. We know that whenever we have cos hyperbolic t, then it is defined as e raised to t plus e raised to minus t divided by 2. Instead of t we have at, so we replace t by at in this formula. Now this is by linearity property, or we can write one more step. This we can rewrite as 1/2 e raised to at plus 1/2 e raised to minus at, and then by linearity property this is going to be 1/2 Laplace transform of e raised to at plus 1/2 Laplace transform of e raised to minus at. So this is using linearity property of Laplace transform, or simply by linearity of Laplace transform. And we know that Laplace transform of e raised to at is given by 1 divided by s minus a, and Laplace transform of e raised to minus at is 1 divided by s minus a. So we are using that formula of Laplace transform of e raised to at, which is 1 divided by s minus coefficient of t. Here coefficient of t is a, here coefficient of t is minus a, and we can take 1/2 common, and we are left inside the bracket with 1 by s minus a plus 1 divided by s plus a. And we know that whenever we are writing Laplace transform of e raised to at equal to 1 over s minus a, we have shown in earlier lectures that this Laplace transform exists whenever value of s is greater than a. So here we mention that s is greater than a. This is valid if s is greater than a. Now we can rewrite this by taking LCM. LCM is s minus a into s plus a, and here we multiply by s plus a, here we multiply by s minus a. So a will cancel out and we are left with 2s, and this is going to be s square minus a square, and all these things are valid if s is greater than a. So finally we obtain that Laplace transform of cos hyperbolic at is s divided by s square minus a square. S is greater than a. So remember this formula. We are going to use this formula in upcoming lectures whenever necessary. Laplace transform of cos hyperbolic at is equal to s divided by s square minus a square, and this is valid for those values of s which are greater than a. In the same way we can find out Laplace transform of sine hyperbolic at using the definition of sine hyperbolic at. Laplace transform of sine hyperbolic at is Laplace transform of e raised to at minus e raised to minus at divided by 2. So here we have used the definition of sine hyperbolic t. If we have sine hyperbolic t, then that is equal to e raised to t minus e raised to minus t divided by 2. Instead of t we have at, so here we replace t by at. Now by linearity property this is going to be 1 by 2 Laplace transform of e raised to at minus Laplace transform of e raised to minus at. So this we have written using the linearity property of Laplace transform. And then we have standard formula for Laplace transform of e raised to at, that is 1 divided by s minus a. Here coefficient of t is minus a, so that is s minus a. So we are using this formula. Laplace transform of e raised to at is 1 divided by s minus a, and provided s is greater than a. So now we have to simplify all these things. This is 1 divided by s minus a minus 1 divided by s plus a, and then we take LCM. 1 by 2 LCM is s minus a times s plus a, and here this one is multiplied by s plus a minus this one is multiplied by s minus a. So now we simplify this. S minus a into s plus a, that is s square minus a square, and here we can rewrite this as s plus a minus s plus a. So this is going to be 1 by 2. Here we have s will get cancelled out, 2 times a, 2 times s square minus a square, and 2 will get cancelled out, and we are left with a divided by s square minus a square. So therefore we have shown that Laplace transform of sine hyperbolic at is equal to a divided by s square minus a square, s is greater than a. So we have obtained the two formulas for hyperbolic functions, and we will remember these two formulas. Laplace transform of cos hyperbolic at is s divided by s square minus a square, and Laplace transform of sine hyperbolic at is a divided by s square minus a square. And before this we have obtained the formulas for exponential function, that is e raised to at has Laplace transform 1 over s minus a, and Laplace transform of 1 is 1 by s. So we have obtained these formulas so far, and we are going to remember all these formulas because we are going to use them in future. So in upcoming lecture we will derive 2 more formulas for cosine and sine functions, and these 2 formulas we have obtained using linearity property. If you wish, you can use the definition of Laplace transform and you can derive this formula. You can go in this way also. Laplace transform of cos hyperbolic at is integral e raised to minus st times cos hyperbolic at dt, and then you can replace cos hyperbolic at by e raised to at plus e raised to minus at divided by 2, and then you can integrate with respect to t. So in that way also you can derive the same formula. We have used the linearity property and this formula of Laplace transform of exponential function to derive these 2 formulas for Laplace transform of hyperbolic functions. So this is all about this lecture. I hope you like it. In upcoming lecture we will derive the formulas for Laplace transform of cosine and sine functions. Thank you very much.